Okay, so let's get started. So that's yours. Okay. So today we are going to, where is it coming from? Is that yours? No. Really bizarre. Are you on Zoom? Where is that audio coming from? Really odd. Just a second. It's actually, it's broadcast. Okay, let me just, okay, maybe that'll do it. Okay. Where is this? Is that still coming? I don't know what is, something is broadcasting. I don't know what. I should use this. How is that? Hold on. I will. Hello? Esto es. Yeah, what is broadcasting? I'll use try this one and see if that solves the problem. Otherwise, we are in trouble. Okay, so this has no audio, so it should not send anything.
Yeah.
Okay. No echo, right? All right. I don't know what was happening. So, okay, so let's get started. Sorry for the technical difficulties. So today we will start a new topic, which is distributed transactions. And the topic is quite related to databases. But what we are interested in here is to see when you take databases and make them distributed, how can you take the concept of transactions and also make them distributed? Okay, and this is going to be an early precursor to several other topics we will study, which would include things like distributed commit, consensus, Paxos, and so on. Okay, so all of those are related topics, and we'll start with something relatively straightforward, which is transactions. Okay, probably have heard the word transactions in a database context. Even if not, I will introduce what this means, what traditional transactions do, and then we'll look at how do you deal with that in the context of distributed transactions. And then we'll end with discussion of concurrency control, which is how can you take queries in distributed transactions and execute them in parallel, and how does locking work in that context. Okay, so let's start with what is a transaction. So transactions have their origin in databases. So it is an abstraction that allows you this concept of atomicity in distributed system. Okay, what does atomicity mean? Atomicity essentially means all or nothing in terms of how a set of operations execute. Okay, so suppose you have a set of instructions, okay, and you want a property where either all of those instructions execute successfully or none of them execute successfully. Okay, you don't want a case where maybe 5 of the 7 instructions execute and 2 fail to execute. Okay, if you do not want such a case where you want either all of them or none of them, you basically have to use this concept of a transactions, because what you will do in that case is you will take any of the set of instructions, you will add a begin transaction and an end transaction around them. Okay, and then the transactional system will guarantee atomicity. Atomicity means it will guarantee that everything that's within the begin and the end transaction, either all of those instructions execute or none of them execute. Okay, and we'll see examples of why this is important in things like databases and so on. But we'll start with why you even need atomicity, let alone the all or nothing property. Okay, so we'll take an example, which is a database example, but it makes the point where of a banking database, there are 3 accounts in this database. Okay, account A has a $100 balance, account B has $200, and account C has $300 balance. Okay, now let's assume that there are 2 clients that are performing some operations on this database. Okay, client 1 wants to transfer $4 from account A to B. Okay, and client 2 wants to transfer $3 from account C to B. Okay, so it should be clear that B is getting $7. Okay, it's getting $4 from A and $3 from C. Okay, so logically that makes sense. But now when clients 1 and 2 actually execute these operations, here is what is going to happen. Okay, so client 1 has to first read the account balance of A, and it has to deduct $4 from it. Okay, and then it has to read the account balance for B, and it has to add $4 to it, right? Because it's moving $4 from A to B. Okay, that's how you actually do it. You read the balance, you deduct or decrement the amount, then you read the other balance, you increment the amount, and you will have to do the same thing for C, where client 2 is going to take $3 and then add it to B's balance. Okay, now because these are now independent read and write operations that are being performed on this database, which has these 3 different accounts, okay, let's assume that they're actually executing concurrently. They are going to get interleaved because client 1 and client 2 are performing these operations at the same time. Okay, and this interleaving could be arbitrary if you don't have any higher level control over what is going to happen. Okay, and here is essentially one possible interleaving. Okay, you will see that, so the y-axis here is time. Okay, so you will see that first client 1's instruction executes and it read $100 from A, then it decremented A. So far everything looks good, but now because of concurrency, let's say the CPU switches to the program executing client 2's query. In this case, it's read C's balance and it decremented $3. Okay, so far everything looks good. You've taken the money from the 2 accounts. Okay, now you got to deposit it into B's account. Okay, so here is one possible thing that might happen. So client 1, in order to deposit it, it reads A's balance. It says 200. Okay, and then the scheduler somehow switches to this other program, and you read B's balance, still 200. Okay, then you increment by 3. Okay, so now this became 203. Then you switch back to client 1. Client 1 has already read the balance, even though it's gotten incremented. So it's simply going to add $4 to B's account. And what you have ended up is basically B is ended up with a balance of 204. Okay, which clearly is wrong, because we were expecting that $7 would get transmitted. Okay, essentially this operation has overwritten the previous write here because they are interleaved. right? And so client 1 didn't know that there was something else happening to B's record, and it just overwrote it. Okay? So if you just simply execute these two things in parallel, you have a race condition. Okay? Now clearly you know, because you've done threaded code and so on, if client 1 and client 2 are threads, you would have put some locks there. You would not have just done this. Okay? This is an example of a race condition. Okay? But normally you would have to do locks, right? But in database world, you don't do locks. What you will actually do is you want to make sure that not only you protect A and B with locks, you want to in fact protect all of those 4 instructions, because if any of these instructions fail for any reason, you want to undo everything, right? So maybe you try to write to B's balance, but maybe the database gives you some sort of an error, okay, for any reason. Okay? At that point, you can't just say there's an error, so you won't finish. You actually have to go undo whatever you did there, because you already took money from someone's account that you are not depositing in the other account, right? So that is why you need the all or nothing property, where you want, first you want consistent results, which these interleaving doesn't do. But even if it were consistent, you want to assume that all of those 4 instructions that client 1 and client 2 are executing, either all of them succeed or none of them succeed. What that means is any one of them fail, you got to undo whatever you have done so far and bring the system back to the original state, which was consistent. Is that clear what I'm trying to say? Very simple example. So it illustrates 2 things. One is that, of course, you can have race conditions and then you get inconsistent result. That shouldn't be a new thing, because you're done locking and other things for threads. This is why you actually implement locks, because you want to ensure consistent result when you modify shared data, which this is A and B and C are the records in a database that are being shared, in this case, between client 1 and 2. But there's a more important and a more subtle point, which is that if there is any failure of any of those instructions, because we are actually transferring money, you want to ensure that you undo everything that has been done so far. That's our all or nothing property, which is also called atomicity. Okay? So that's something you have not done, because when you write threaded code, you are not guaranteeing atomicity. You are just protecting shared data structures with lock. But sometimes you want higher level properties which say, I want all of these things to succeed, not just some of those instructions and then others give an error, right? So that brings us to this notion of the transactions and properties that transactions give. And these properties are very well known using an acronym called ACID properties. Okay? So that's an acronym. ACID, essentially, A stands for atomicity, there's consistency, I is isolation, and D is durability. Okay? So transactions actually give us ACID properties, and so let's go through each of them. Okay? Atomicity I already talked about. It's the all or nothing property. Whenever you have some instructions that are enclosed in a transactions, okay, the transactional system will guarantee that all of those execute, okay, as a single atomic block, or none of them execute. So if something goes wrong, it goes and undoes whatever has been executed. That's atomicity. Okay? Consistency says that if you have your distributed system or a database in a consistent state and you execute a transaction on it, if the transaction succeeds, then you take it to another consistent state. Okay? That's another way of saying, in the previous example, okay, where we talked about the data, that we have a variant of that here, we were making operations on 3 accounts. Initially, everything was consistent. At the end of this, even though you might have arbitrarily interleaving, you still want the account balance to be consistent with what you are trying to do. Okay? I showed you an example where the race condition left it in an inconsistency. This is not consistent, because this is not what you had expected if you are running those 2 transactions. Okay? So you wanted that balance to be 207, for example. That would be a consistent state. Okay? So that is another property that you will get from transactions. Isolation essentially means something called also called serializability. Okay, so what this says is, even though the transactions are actually executing in parallel or in concurrently, okay, we want their output to look like they executed sequentially. Okay, because that's the way we will actually assume concurrence. So in other words, if you look at this interleaving, this basically says client 1 goes first. Okay, it does all of its 4 operations, and then client 2 goes next and it does all 4 operations. Or you could have reversed them. Client 2 could have gone first and client 1 could have gone second. Those are the 2 sequential executions of those 2 transactions. Okay? And even though that's not how you will actually execute them. There will be arbitrarily interleaving. Okay, the output will look like either you executed client 1 followed by client 2 sequentially, or client 2 followed by client 1, even though they are not actually executing sequentially. Right? That property is called serializability. It says that you can serialize the transactions even though they're executing in parallel. And if you serialize them, that's equivalent to each client taking a global lock, executing its thing, then you take the next lock, and so on. That's what, if you actually put a global lock, you will get. Okay? So even though we are not going to put global locks and we will execute them concurrently, you want the transaction to be serializable. Okay? That's a property. It's also called isolation property, which means that it looks like only one transaction is executing at any given time. Okay? That's what it means. Okay? So that's isolation. And durability means once the transaction finishes, once you've written your records, okay, then you cannot undo anything. Okay? While you are executing these instructions, you have the ability to undo, which is called rollback. Okay? But once you have committed the transaction, once the transaction is successful, then you cannot undo it, because you said it's done. You cannot go back and say, let's undo what it did. Okay? So those are the 4 properties that transactions give you, any transactional system. Okay? Particularly relational databases and others, and many types of distributed systems also that have transactional semantics will give you this property. Okay? From our perspective, really atomicity, consistency is more important. We will talk about serializability as well. Okay? Is this clear? These are just definitions. We haven't said how to do any of this. Okay? But these are all good properties to have. It allows you to implement higher level code in large concurrent systems and reason about it without worrying about race conditions and whatnot. Okay? Much more higher level than taking individual locks on data structures or shared data and so on. Okay? All right. So let me now give you some simple examples before we think about how are we going to implement at least few of those properties, not all of them. Okay? So here is essentially how you write a transaction in a distributed system or in a database. Okay? Essentially, you can write arbitrary code. You can write code in Python or Java, or maybe if it's a database, you'll write it in some language like a query language like SQL. That doesn't matter. Okay? If you want to implement a transaction on top, you really have to have these 2 statements, begin transaction and end transaction, and any code that you put inside it, the transactional system will guarantee ACID properties on it. Okay? So you can just take any code and just write a begin and an end transaction. And of course, if for any reason you want to kill the transaction in your code, you have to call the abort transaction, which will then undo whatever has been done since the beginning. Okay? You will go back and essentially undo the change. Okay? That's how you are going to write your begin and end transaction. Read and write, you don't actually write code about, you just write higher level code. Internally, the transaction reads and writes either from a database or a distributed data store and so on. Okay? Here is an example of a transaction, and now you will see why you need an all or nothing property. Okay? This example is trying to book a flight. Okay? The flight goes from New York to Delhi, but there are intermediate hops in the flight. Okay? So the first leg of the flight says you go from New York to Paris. The next one says go from Paris to Athens. The third one says goes from Athens to Delhi. So there are 3 legs to this flight. Okay? Now, for the booking to be successful, you need all of the 3 segments. You cannot make the trip if only 2 of the 3 segments work and the third flight is full or something like that. Right? So this requires all or nothing. So what you will do is you will write a begin and an end transaction, and you'll say, if go and reserve from New York to Paris, if that is full for any reason, then abort, because then you can't make the booking, at least for this routing, right? And then if that succeeds, then go and do the next segment. But if that fails, then again undo everything you've done so far, and then go and reserve the third segment. Okay? And if all 3 succeed, the transaction has succeeded. If any of them fail, you'll use the abort to kill the transaction. Is that clear? Very simple example from databases, but now you know why you need all of those 3 or none of them, because there's no point in having one segment, then you can't make the trip, right? Okay. So now let's take that very basic knowledge and try to think about making things distributed in some shape or form. Okay, there are 2 ways I will discuss how you can make things distributed. One is called a nested transaction. The other is called a distributed transaction. Okay? A nested transaction is an example where your trip involves multiple databases and you want to make multiple transactions, but then have a parent transaction that envelopes this transaction. And here's the example. Okay? You want to make an airline booking and you want to make a hotel booking. Okay? The hotel database, let's say, is separate from the airline database. Okay? So you will have one transaction to book your flight. You'll have another transaction to book your hotel, but you want both of them to succeed. If you have a hotel with no flight, you can't travel. If you have and vice versa as well, right? So you will take each of those transactions and then you'll put a begin and an end around it. So these begin and end transactions have two smaller transactions inside them, one for your airline booking and one for the hotel booking. Okay? These are called nested transactions because one transaction is nested inside the other, and you want both of the small transaction to succeed and the big transaction also succeeds. Okay? So this is called nested transaction. Okay? So that's one example where we made things distributed. Here you're just distributing it across multiple systems, okay? And then having a transaction around whatever you're doing within each system. Okay? The second example is where you have one database, okay? But that database is large in size, so it doesn't actually completely reside on one machine. Okay? Maybe you have lots and lots of data. Okay? So your database is split and it is on multiple machines or multiple disks on multiple machines, as is shown here. Okay, those two gray things are actually disks, they represent machines. And then there is a logical disk that's around it, which says that the database is a collection of this distributed data across machines. Okay? Now, if you are making a transaction on this logical database, okay, and that transaction operates on some data in the first machine and some other data on another machine, you still want your transactional properties. You want your asset properties around all of the operations you perform. These operations are now spanning multiple machines. Okay? So each of them will be a sub-transaction, which is the work you will do on these independent machines. Okay? And you want all of those things to succeed. Okay? So this is a little bit different from a nested transaction because this is still one transaction, but it's operating on different machines because some data is on machine 1 and some other data is on machine 2, and you want to take the whole thing and make it a transaction. Okay? This is a distributed database. Okay? And you are now giving transactional properties that span machines, as opposed to normal databases that are actually single machine systems. Is that clear so far? Any questions on this? Okay. So now let's talk a little bit about how will you implement a transactional system. Okay? I'll give you two simple approaches. Okay? One is called a private workspace, which is actually talked about here. And then the other one is going to involve in-place updates. Okay? So let's start talking about one of them at a time. Okay? So remember, the transaction needs to have the ability to undo whatever it's done. Okay? That is why you get atomicity. So both of these are going to talk about atomicity in particular. Okay? So the question is, how are we going to make sure we have the ability to undo? Right? Because you are going to actually go and make active changes to the database. And if the transaction fails for any reason, you got to undo everything you've done. So you need to restore the database to its previous state. Okay? So here's an example. Okay? Here's an example database, which is very simple database where there are 3 items: data item 0, data item 1, and data item 2. Okay? And then the database is going to have an index which allows you to point to where the data is stored on your disk. Okay? All databases keep an index stored to file system. Okay? Now suppose that you write some code that goes and modifies one of these data items. Let's say you go and modify 0. Okay? Normally, you'll just go and overwrite whatever was stored there. Right? Maybe that was grades in a grading database or some other information. So if you want to update this record or it's a bank balance, you'll just go and update that piece of information. Right? Now, once you've done that, whatever was there and that record previously is gone because you went and overwrote it. Right? Because you went and updated someone's bank balance. Now the old data is gone. You now have a new balance there. Okay? But if the transaction fails, you got to go and undo it. Okay? So somehow you have to keep track of what was there before you made the update. Otherwise, there is no way to do an undo. Is that clear? So even though you are changing, so just think of it as you go open a file. Okay? You go and modify some lines of code. Okay? And then you save it. But let's say it was a transaction and you say, I want to kill the transaction. Somehow you got to go back and take all the changes that were made to the file and remove them. Okay? But if you already wrote it, all the old changes are gone. The file has changed on this. So the only way you're going to undo it to track what was there before. Okay. So to do this, we are going to actually figure out a way to implement what is called a private workspace. Okay. So what is a private workspace? Private workspace is you have a database. Okay. Whenever you start a new transaction, okay, make a copy of the database. Okay. So you just have a database to when you have a begin transaction, you make a full copy of the database. So now I have a second copy. Okay. The transaction then operates on the copy. Okay. All of the changes are made to the copy of the database. Okay. Now, if the transaction has to abort, you just throw away the copy. You never change the original data, so it's there as is. Okay. So there's nothing to undo because you never changed anything. You are operating on a copy. Okay. But on the other hand, if you decide the transaction is successful, you are going to take the changed copy and then you are going to essentially call that the new database. Okay. Or in other words, you can think of you took the copy and you reflected all the changes in the original database. Now all the changes have appeared in the database, you're done. Okay. So this is called a private workspace. Every database transaction that you will execute, you will make a copy of the database. Okay. The transaction will make changes only to that copy. And if you want to throw it out, then nothing has to be done to the original database. The transaction succeeds, you will reflect the changes. Yes, question. Okay. What happens to concurrent writes on the same database? We will get to that. Okay. At the moment, we are not worrying about it because the assumption is if you have private copies, you will make changes to your individual copies, and somehow that has to be reconciled when you merge the changes. Okay. But we will talk about that. Okay. Is this clear? Yes. Yes, that was going to be my question, saying, yes, this is a good idea, but looks a stupid idea because I said make a copy. The 100 gigabyte database, every time you make a transaction, you are not really going to make 100 gigabyte data copy. Okay. So you got to do this efficiently. Okay. So what is the way we are going to do this efficiently? Okay. We are going to use a pretty standard approach that is used in operating systems, which is called copy on write. Okay. It's also called lazy writes. I think I had mentioned this some time ago. Okay, I said we'll come back to it. This is where we actually now see why it's very useful. Okay. So what is copy on write? Copy on write says that when you make a copy, you don't actually make the copy of and copy all of the data. We'll create a virtual copy. This is what we had talked about when we did snapshots. Okay. And I'll show you an example of what a virtual copy is. Okay. And we will only make changes. We will only make real copies when some data is modified, because that's the only thing you have to track. Data is not read or written to, you don't really need to make a copy at all, because that the transaction is not touching the data. Okay. Let me make this more explicit with an example. Here is, okay, and it's just the second thing here in the figure shows you what is a private workspace. Okay. So we'll say the original index is pointing to 3 data items. That's your original database. Okay. When you make a private workspace, you don't actually make 3 more copies of this. That was what a real copying would mean. Instead, you just make a new index, and those index point to the same 3 data items, 0, 1, and 2. Okay. So now you have 2 indices that are pointing to the same data item. Okay. One of them is the original data, the other is the private workspace. Okay. And the private workspace has access to the same data as the original until you start making changes. Okay. Now when the transaction makes a change, let's say it goes and updates data item 0. This is where your private copy has diverged from the original database because now you made a change. Okay. So what you will do is, this is where you will actually do copy on write. You will say 0 has changed. So now you actually make a copy of 0 and you will make the change in that copy. Okay. And you will update the private workspace. So you will see that the private workspace now points to 0 prime, which is the new version of 0. The original data is still pointing to 0, 1, and 2. So it is unchanged. Okay. So you only took whatever you changed and made a copy, and then you updated the pointer. Okay. So the private workspace now points to the new version. The old one is still pointing to the old version. Okay. And in fact, it shows you that you added a 4th data item, which is 3 prime, and then you basically made a pointer to 3 prime here. Okay. So now the private workspace, okay, has 1 and 2 that's unchanged, and you will see that both of the original and the new one just point to the same 1 and 2. They have pointers pointing, because that's unchanged data. There's no need to make a copy. But anytime you add new data or you make a copy, you are going to do this copy on write, which essentially means what it says. You make a copy when you write to it, and you write to the new version, so the original is preserved. Okay, is that clear? All right. So now let's say that's your private workspace. Okay, one of two things will happen to this transaction. Either the transaction will succeed, or you'll say, I want to throw it out. Okay, I want to undo all the changes because it has all or nothing property. Okay, so now we have the same thing that I talked about when I said you make a full copy. If you want to discard this data because you want to abort the transaction, you simply go and delete that index, delete all the new changes you made 0 and 3, and then the original index is still pointing to 0, 1, 2, so nothing has changed in the database. Okay, so you undid it by just throwing away the copy. Okay, here throwing away the copy essentially means only throw away the changes that were made because none of the rest of the data was touched. Okay, so it's still simple. It's a virtual copy. You threw it out. Okay, but on the other hand, if you want to commit the transaction, you will merge the private workspace with the original database, which means the original database, that 0 pointer will be updated to the new 0, and 3 gets inserted there. So now the database has reflected those changes. Okay, and now you have the new version of the database having all of your updates. Okay, modulo the question that was asked, if two transactions modify the same data, we have to deal with that conflict. That is not shown here. We'll get to that. Okay, this is showing one transaction. Yes, question. Okay, this question, does it require you to copy the entire index? Yes, virtual copy is required to copy the entire index, but not the original data. And the assumption is the indices are much smaller and easier to copy than the data itself. Okay, otherwise it would not give you any savings. Any other questions here? Is this clear? Private workspaces. Okay, so essentially you make a copy, you modify the copy, and then either you throw it out if the transaction aborts, or you merge the changes into the original. Okay, and the only thing is you got to be smart. You're not going to make a real copy. You'll make virtual copies using copy on write techniques. Okay, most operating systems will have this because that's the way they are going to do efficient copying of large amounts of data. Okay, so you leverage that to do this efficiently. All right, that's technique 1. Okay, here's another technique. Okay, this technique is actually not going to make a copy of the database. It will let the transactions go and make changes directly to the database. Okay, just as I had said originally, you go and start modifying the database. Okay, but you still need a way to go and undo your changes. Okay, so the way you are going to do that is you keep some extra information with the database. Excuse me, which is called a write-ahead log. Okay, you will keep a log of changes. Okay, the log keeps track of what changes have been made to the database by each transaction. Okay, so now if you have to undo the changes, you go to the log and you track what changes were made, and you are going to undo it. Okay, but on the other hand, if you want to commit the transaction, there is nothing to do because the changes are already in place. You went and modified the database live. There was nothing that you need to do if you want to commit because the data has already been modified. But if you want to undo, you are going to go to the log and look at whatever has happened, and then you are going to undo it. Okay, the log is going to at least keep this following information. Okay, it will have a transaction ID because there will be multiple transactions. It will track whenever you change a block or a record, it will track the block number. It will keep the old value and it will keep the new value. Okay, so you are going to keep a record. So this log is going to keep all of this information for every transaction. When it makes a modification, it will say this transaction modified this record or this block. This was the old value of the data. This is the new value of the data. Okay, all of that is going to be stored in the log, and I'll show you how you can use the log to undo the data. Okay, there's nothing to be done if you are going to commit the transaction because the changes are already there. Okay, but if you have to undo it, then you have to go to the log and actually do what is called a log replay to roll back the transaction. Okay, is this clear what I just said? Okay, there's a more straightforward approach where you don't need to make copies. You're directly making changes, okay, and writing them to disk, but you keep extra information to undo, which is your log. Okay, we look at an example. Yes. Okay. So commits need to be atomic. We'll get back to this. This comes back to consistency. We have not talked about consistency because none of this is actually talking about locking as yet. Because the only way you are going to make sure the changes are consistent is there have to be locks on top of everything, so you can figure out when there are conflicting changes being made. Okay? For now, we will not worry about it, but we'll look at that problem in next few slides. Okay? Here is very simple example. Is a question there? Yes. Can undo fail? Okay, the assumption is undo should not fail. Otherwise, you will not get ACID properties. Okay? So if the undo fails, then your database is left in an inconsistent state because you are starting in an inconsistent state. You did a transaction, you want to undo it, and then it did not work. Okay? Typically, transactions don't fail because there is something wrong with the hardware. They fail because higher level logic, that one segment of your flight is not available, so undo it all, that type of stuff. It's not like the file can't be returned to because the disk filled up or something. That's not the reason things fail. Okay? So hopefully, as a result, undo should not fail. Okay? If it does, then we have other problems. Yes, questions?
The logs are maintained again on the transaction.
Yeah, the question is, how long are you going to keep logs? So typically, the log is just a file that you keep writing to. Okay? Once the transaction is finished, you can actually throw away the changes from the log. But databases will typically not do that because it's extra work. So you just keep writing to the log. Once, let's say, the log grows to a certain size, you will just start a new file and start writing to it and eventually throw out the old file. Okay? That's better than going and trying to remove things, because that's even more things you have to write to disk, and disk writes are slow. So the idea is you don't want to do unnecessary things. It's just useless information in the log. Eventually, you will just throw out the entire log because you started a new one. Okay? So maybe every night you start a new log, and then old days changes are thrown away. That's the way databases will work.
Logs can have logs in multiple transactions.
Yes, so I'll show you. Yes, so because there are multiple transactions executing, you write each transaction will just write one line. Okay, so there will be interleaving of different transaction updates. Okay, but when you want to undo it, you will look at the transaction ID. You will only undo those changes, not those by other transactions. Okay, so here is an example. Very simple one. The database has only two values, X and Y. Okay? For simplicity, I'm just showing you this as code, but think about this X and Y as being two values stored on a disk in some database. Okay? This is our transaction that's going to operate on X and Y. Okay? We just say X is X plus 1, Y is Y plus 2, X is Y times Y. Okay? And then there's a begin and an end. So all of those three things have to work, or none of them have to work. Okay? That's the rule. So here is basically, as this transaction executes, this is what's getting returned to the log. If the first transaction goes and increments X by 1, okay, so you would put a transaction ID, which is not shown here. Then you say X was changed, old value is 0, new value is 1. You write this to the log. Okay, and then you actually change the value of X to 1 because you are making in-place updates. Okay, and the second instruction will execute, it increments Y from 0 to 2. So you'll write that second line to the log. And the third one is going to run, and you are going to write X went from 1 to 4. Okay. Now let's assume if the transaction commits, then we are done. There's nothing to be undone here because you already made the changes to X and Y. But let's say after the third instruction, for some reason, you decide to abort this transaction. Okay. X and Y are no longer at 0, 0. They are in fact 2 and 4. Okay. How will you undo it? Okay. This is what is called rollback. So you have to now read the log backwards and replay all of the instructions that are written in the log. So you will undo it. Okay, this is how it will work. So the log has 3 lines. Okay, there will be other lines from other transactions. We ignore those. This is the one that's being undone. So you will say, okay, X is 4, reset it back to 1. Okay, so you'll go and write 1 back to X. Okay, and you will go to the previous line and say Y is 2. Reset it back to 0. Okay, now Y is gone back to 0. Then you'll go back to the first line and say X is 1, make it 0. Okay, now you replayed this log backwards. You undid all the changes. X and Y are back to 0, 0. Okay, so now you undone the transaction. Okay, so all you got to do is not have to do much at all. Whatever you wrote in the log, you just replay it backwards and you undone all the changes. Is that clear? Any questions on this? Okay. This is called write-ahead logs. This is another way to implement your transactional systems. Okay? Neither of these two approaches so far have anything to do with locking and so on. We'll get to that. But it's just showing you two ways by which you can give all or nothing guarantees. Right? So you can implement a transaction, commit all the changes, or undo them all. Questions here? Okay, this is going to work regardless of whether you have a centralized database transactional system or a distributed one. Okay, private workspace and logs are going to work in either case. You'll have to keep those two pieces of information, not pieces of information. You use one of those two techniques, either keep logs, okay, or keep private workspaces. Yes.
Is it database where it's been logged, you have a unique record ready that records previous and updated values?
You're asking about write-ahead logs. Okay, how will it work in a database? So in a database, you have the database file which actually has data. Okay? There'll be a second file stored on disk which we'll call the log file. Okay? Whenever you have to make a change to the database, the rule is you have to actually write to the log file as to what changes you are making. So if you are going to go and update X to 1, that's a change you want to make to the database. You'll first go to the log file and write this line out, saying that I am changing the value of X to 1, and then you go make the change. Okay? So your log file will be written to when you concurrently when you write to the database. Okay? So you keep making changes to the database, you keep also writing to the file. Okay? Whenever it's time to abort a transaction, you will go and look at all the entries in that log for that transaction and undo it. The transaction commits, there is nothing to be done. So you will just keep writing other transactional information. Okay, question is it a text file? You can think of it as a text file, but if the data in the database is binary, then those values have to be binary blobs. Okay? But if they're numeric data, that depends on the database, of course, right? Your database of images or something, and you update an image, you have to keep the old and the new version, right? But if it's just numeric values, it will be textual information. Okay? But whatever it is, the thing is, you have to keep track of what data you change, the old value of the data, the new value of the data. Whether it's numeric, whether it's image, we don't really care. You just have to have both of those values written in the log. Okay, so question is what are X and Y? No, X and Y are the two values in my database in this case. It's not an index. This is a database of two entries. One is called X, the other is called Y, right? So you could have thought of them as bank balance of X and Y or some whatever you want to interpretation in. So that's not an index. Those are actual values in the database. Okay, so can you explain you're saying that there are many transactions and all of them get aborted? Is that your question? No. Yeah, that's a good point. Question is, how do you know that you rolled back all of the instructions of the transaction? That's a very good point. You do have to write when a new transaction begins, saying transaction XYZ started. When it ends, you have to say transaction ended and committed. You'll write that extra information. Otherwise, you'll keep reading the file all the way to the beginning needlessly. If you hit the beginning of the transaction, then you can, yes, you will have to write that extra information. Okay, any other questions? All right, so now we'll talk about how will you let multiple transactions actually work on the database. Okay, how are you going to ensure good performance and so on. Okay, so database should be clear is a big shared data structure. All of the entries in the database, okay, whenever you query it, they are all essentially going to be potentially read or written. Okay, no different from your lab 2 where you have an order database and you are keeping track of stock information and so on. Okay, you are just keeping them in flat files, but think of those as some type of a database. Okay, now what is a good way for you to protect this data when you try to access it? you put a lock around it, right? So this is going to ensure that when one in your lab example, maybe one customer is trying to buy some stock, okay, some other customer doesn't come and do make some conflicting operation. So you will put a lock, right? Now, if you implemented that approach for large databases, your performance is going to suffer, okay? Because you will say, take a lock on the database, okay? Then go and make your airline booking, okay? Release the lock. That's what you will write, okay? But imagine now there are thousands of users trying to book tickets. They all have to become sequential transactions. The person who says buy will have to wait for a while because maybe there are 150 other users ahead of them, and each of them have to be processed sequentially, right? So sequential processing of transactions is going to be very bad from a performance standpoint, okay? So you don't want that, okay? But if you put a global lock, that is what you're going to get, right? You put a big lock, so the entire database is locked by one transaction. So nothing else can execute by definition. Everything else is sequential, right? So you don't really want that. What you instead want is for these transactions to execute in parallel, okay? Yet you want correctness guarantees. Okay, what are our correctness guarantees? This is where we'll get to serializability, okay? So you want to make it look like these transactions executed one at a time, as if they had a global lock, because you know that is going to always be correct, right? But you don't really want to take a global lock. You want to let them run in parallel so that many users can make their booking at the same time, okay? And you will not get very bad performance on your database, okay? So this is where you are supporting concurrency, okay? So correctness requires that you only have one transaction executed at a time, but that doesn't work for performance. So you want somehow to have concurrent execution, but you want the results to look like as if they executed one at a time, okay? So that's going to get us to serializability. But let me show you some high-level aspects of concurrency control, and then we'll look at some simple ways to actually do this, okay? So here is how transactional managers actually work, right? So you have this begin transaction and end transaction on your database instructions or queries, okay? And then the transaction manager, as it's executing, it actually tracks what data item is being modified, okay? And it takes logs specifically on some small number of data items, not the entire database. That's going to make the whole thing sequential, okay? But what you can do is you can say, I want to just take a lock on, let's say, the balance of user A, bank balance of user A, or I want to take a lock on the user. So you are locking individual lines of the database, okay? Individual records of the database, not the entire database, okay? So that's how transactional systems will give you concurrency. So if two transactions are working on two separate parts of the database, they can both grab locks on different items. They will not conflict. So these transactions will operate in parallel, okay? The only issue will come up when two transactions work on the same data, in which case only one transaction should really succeed, because otherwise you might have problems, okay? But lots of times, maybe some user is making a flight booking to go from, let's say, New York to San Francisco, and someone else wants to, let's say, go from Boston to Miami. These are different flights. There is no conflict. So these transactions can take locks on individual records. There is no problem. You got concurrency, okay? So this is how we are going to achieve concurrency, by doing more fine-grained locking-based operations, okay? How to do that we'll talk about, but that's the basic idea. So you will have the transaction manager internally takes locks and releases locks, and then you are actually going to make changes to the database, which is your data manager at the bottom. So it's a three-level structure, okay, where the user is only writing this part, okay? In all of these other things are happening internal. User code never takes locks. You just write begin and end transaction. Let the transactional system deal with this. Yes, your question. Okay, how do you deal with it when the database is replicated or distributed? So here is an example of what you are asking. So let's say this is a 3-machine database. It's either distributed or replicated. So your transaction manager is going to sit at the top, okay? And then it has to grab locks on data on multiple machines. So in your example where you said, what if the data is replicated? If there are 3 copies of record A on 3 machines, you have to get 3 locks in this case. That's the only way you're going to protect all of them, okay? So essentially, but that's up to the transactional system to know what is the data, where is it stored, what locks to get, and so on. Users don't need to worry about it. That's the good part. I mean, it's all done internally by the system. Okay, question is, in case the data is replicated, if you make a change, you copy it to the others. Is that your question? Right. So whenever you have replication, and we'll get to replication in a lot more detail in maybe 2 or 3 lectures, but whenever you have replication, an important aspect of replication is consistency. Consistency means that all copies have to be kept consistent with one another. You can't have one copy where you updated the bank balance. That bank balance is replicated on 2 machines, you didn't update them. Then you're out of sync. You're inconsistent. Okay? So whenever you make changes to replicated versions of data, you have to make sure the change propagates to all of them before the transaction finishes, so that all 3 copies in this example are consistent with one another. Okay? So those are all things you will have to deal with, both at a transactional level, but also there's going to be some replication logic that will be in there. Okay? But before we get there, we should understand how you are going to get these locks and how will we implement concurrency and so on. Okay? And then we'll get to replication and other things. All right. So we'll start with serializability concept, so you at least understand what it means. Okay? And then we'll see how do you do concurrency control. How are we going to grab these locks and let all these transactions execute in parallel. Okay? So here are 3 transactions. Okay? It's a very simple database with one data item, X. Okay? That's all there is in the database. Single data item, all 3 transactions are modifying X. You can see that. Right? So the first transaction sets X to 0 and increments it by 1. The second one also resets it to 0, increments it by 2. Third one sets it to 0, increments it by 3. Okay? Now we will assume that these 3 transactions are going to execute in parallel. Okay? So the first question we should ask is, if they're executing in parallel, what values of X are we willing to accept as being consistent after all 3 transactions have finished? Is the question clear? Okay. So you have one data item in the database, X. Okay. All 3 data transactions are modifying X. They're all running in parallel. Okay. And then at the end, let's say I show you some value of X and I ask you, is this a consistent execution of these 3 transactions? Okay. So the question is, what values of X will you accept as being consistent? Okay. So this is where you have to assume, not assume, think about serializability. What does serializability say? Serializability says that forget that are actually executing in parallel, pick some sequential execution. Okay? And any sequential execution is acceptable. Okay? Because you could say transaction A ran first, then B ran, and C ran. In this case, you'll just actually execute them sequentially, and you'll say, I will take X equal to 3 as my value because that's what X is at the end of the third transaction. Okay? Or you can assume the opposite, saying C ran first in a sequential order, then B ran, and then A ran. Okay? In this case, X will end up being 1, and you will say that's acceptable because that's a sequential execution of those 3 transactions. Okay? So you can pick any sequential execution. Okay? So you can do ABC, ACB, BAC, pick any sequential execution, and whatever you end up with is acceptable. Okay? So that's what serializability means. Whenever n transactions are executing in parallel, if you are given some end state after those n transactions finished, if you can find one sequential execution, any interleaving that gives you that output, you will say that's acceptable. Okay? Which means that there was at least one sequential execution that would have produced that result. Which one will actually result, we don't know, because they're actually executing concurrently. Okay? But we'll say pick. So you look at the output and you can then analyze any order and say that order gives me that output. If they executed sequential, you'll say that's fine. Okay? But if you find that there is no sequential interleaving that gives you that output, you say that's inconsistent. Because no matter which sequential order I pick, I'd never get that end result. So then this is not acceptable. Okay? Because we want the transaction to be serializable. That's our ACID property. Okay? Even though they're executing in parallel, we want the output to be sequential. Okay? As if they were sequential, not really sequential. Is that clear? Okay. So now with that background, here are three interleavings. Okay. And the question is which of these interleaving is actually allowed as per serializability and which one is not. Then you will understand what I just said, which one will be accepted and which one not. So you will say here is the first interleaving, because it basically is executing A, B, and C. If you look at it and you end up with x is equal to 0 and then x ends up with 3. So this interleaving outputs x is equal to 3. You'll say that's fine. Okay, we know an execution order which is A, B, C, that gives me x is equal to 3. So that's an interleaving we will accept, even though the transaction may have executed in parallel. Is that clear? Okay. So let's look at the second example. Okay. Here what has happened is the 2x is equal to 0 execute first, then you go x is equal to x plus 1, x is equal to x plus 2. So these two go next, and then the third one executes, and you're still left with x is equal to 3. Okay. So what happened in the middle, we don't care. You start with a consistent state, you ended up with x is equal to 3. You say that's an interleaving. I can look at A, B, C gives me that x is equal to 3, so we'll take it. Okay. All right. Last one. You'll see that here you do x is equal to 0 twice, then you increment x, then you do x is equal to 0, and then the last you have x is equal to x plus 2 and x is equal to x plus 3. So you end up with x is equal to 5 in this case. Okay. Now you can pick any interleaving you want, any sequential interleaving. You will find that no sequential interleaving will actually output x is equal to 5. Okay. Because in each case the transaction resets x is equal to 0 and then either adds 1, 2, or 3. So whichever is the last transaction will either get output either 1, 2, or 3. There's no interleaving that will output 5. Okay. So if your interleaving actually ends up with x is equal to 5, you will say that is not a serializable order, so we will not accept it. This is not actually guaranteeing me acid properties. So you have to actually reject that change and not take it, or the transactional system has to reject. So first of all, it probably shouldn't even end there. But if it did, then you have to reject it saying something went wrong. So this is not serializable. Is this clear, what I just said? Okay. So the basic idea of serializability is that because we want transactions to execute in parallel, we will let them execute in parallel. You will see that there are arbitrary ordering of these instructions happen. And then you look at the end result after they've all finished and you'll say, let me look at this output. If that output matches some sequential execution, you will take it. If I can't find any sequential execution, you say it's not serializable and you reject it. Okay, you have a question there? Yes. Yeah. So the second case is, the question is interesting to look at. In the second case, you will see that the interleaving is not actually sequential because you have x is x plus 1 and x is x plus 2. So you have actually gone off, become a little inconsistent, but that should not matter, because what matters is what comes at the end. You are not worried about what happens in the middle. So in this particular example. Yes, so basically you start with the consistent state, you run some set of transaction, you end with some state, and you say, can I have gotten that state with some sequential execution? The answer is yes. You don't care about what has happened in the middle, because you went from one consistent state to another. That's what acid properties say, right? So you don't worry about the middle, you only worry about the end. Okay, that clear? Okay, so this should give you some notion of what serializability does. Okay, the point is now we are beginning to execute transactions in parallel without taking any global lock, and yet we know which output we like and which output we reject as per serializability. Okay, now of course there are other problems because we did not use locks. You might have read-write conflicts, you might have write-write conflict. We'll see some of those. In this case, okay, we didn't see any particular conflicts. We just saw some legal orders and illegal orders from a serializability perspective. Okay, so now the higher level question is, what should we do in the transactional system that lets us do this kind of parallel concurrent execution, okay, to get higher performance and yet end up with valid state? Okay, so here is one approach. I'll talk about 2 or 3 approaches. First approach is called optimistic concurrency control. Okay, so optimistic concurrency control says, let's not worry about locks. Okay? There is no locking in the system. Okay? Transactions will execute in parallel. They will do whatever they want. Okay? We will validate at the end of each transaction, okay, whether the transaction actually has left the database in some consistent state or you're in some inconsistent state. Okay? In particular, you will check if any data that is modified by that transaction was modified by some other transaction. In this case, there is a write-write conflict because if you had taken a lock, okay, only one of those transactions would have modified the data. Because you said I have no locks, two transactions went and modified the same data and potentially overwrote each other. Okay? So if you detect a case where when a transaction is about to finish, any of the data it has touched, okay, was also touched, means read or written by some other transaction, you say that's a conflict. Okay? Because if there was a lock, this would not have happened. This transaction would have locked those data items and prevented that other one from even touching it in the first place. Okay? So in this case, you will just throw the transaction, you'll abort it, saying this transaction caused a conflict, so you abort it. Okay? But on the other hand, if the transaction did not have any of these issues where any data it has touched was also touched by other transaction, then you're done. You go and commit the transaction because you know no other transaction touched that data. So there cannot be any consistent issue by definition. Okay? So this idea works really well with private workspaces. Okay? You give each transaction its workspace. Okay? This goes back to that question that you had asked earlier. So here you will not have locks. You will have workspaces. Okay? When the transaction finishes, you see all the changes that have been made, and you see has any other transaction touched that data. If so, you throw it out. Okay? If not, you commit the transaction and you're done. Is that clear? Okay? So what I showed you is a way to now implement concurrency control with no locks. Okay? Because we are making extra checks at the end of the transaction saying, is there a conflict? Okay? If there was lock, that conflict would have been avoided in the first place because the locks would have prevented it. But we said we don't need any locks. We'll just avoid locks. Okay? And instead, we'll just let the transactions execute concurrently and we'll check at the end. And if there's a conflict, we will abort the transaction. Okay? If not, we are done. Okay? So why does this work? So the reason it works well is that conflicts are typically rare. Okay? If you have very large databases, you have lots of transactions, they might be touching different parts of the database. If they're touching different parts of the database, they are actually not conflicting with one another because transaction one, maybe as I said in the flight example, making a flight booking from New York to San Francisco, transaction two is doing something else. They don't conflict. So there's no need to get locks or take global locks or anything like that. These transactions can execute and there are no conflicts to begin with in this case. So then you're done. Okay? So if this observation is true, it's not always true, but if the observation is true, which is conflicts are rare, databases are large, different transactions touch different parts of the databases, okay? So hence conflicts are not going to be very common, then this is a good approach. Okay? It's a good approach because you got rid of all locking overhead. Okay? By definition, there is this approach is deadlock free. Okay? Is it clear why it's deadlock free? There are no locks, so there cannot be a deadlock, right? So there's no need to worry about deadlocks. Okay? It gives you maximum parallelism because no transaction will block waiting for a lock. Okay? That's the only way you will reduce your parallelism. Here, there are no locks. So it gives you high throughput, maximum parallelism. Okay? So those are your advantages. Disadvantages are you have to rerun the transaction if it aborts. If there's a conflict, you will kill the transaction and restart it. Okay? So that's wasted work because you have to abort the transaction due to conflicts that you detected, and then you have to do extra work to restart it. Okay? And the second thing is that probability of conflict will rise as the load on the system goes up. Okay? Because when the load goes up, there are lots of transactions in the system, so the probability that any two transactions that are executing at the same time, okay, conflict with one another goes up. Okay? When there are few transactions in the system, chances of conflict are low. When there are more transactions in the system, the probability of any two transactions touching the same data item goes up. Okay? So this basically approach is going to give you higher rates of transactions failing when the load rises. At low moderate loads, this is a great approach because you will get high parallelism without any overhead of locking or anything. This is clear. Okay. Very simple approach. Okay, gives you good concurrency. It's called optimistic concurrency control. Okay, because it doesn't use any locks. Okay. Not widely used in practice. Okay. The reason is that banking on the system load being low and the conflict rate being low is not a good design decision. Okay. Because if you run your system at a high load, okay, you will see that lots of transactions start failing. The system load remains high because it keeps rerunning the transactions over and over again. They keep failing, but the system as a whole does not make progress. What is called the good put of the system, which is useful throughput, is going to drop because you are just doing all this wasted work on execute the transaction, abort it, re-execute it, abort it, and so on. Right? So as a result, to avoid this type of problem, commercial databases do not take this approach. Okay? This is a good approach in certain cases, but they are not widely used in the database world. You have a question? How is it aborted? So you have, if you have private workspaces, you can just throw away one of the transaction changes, right? Or you can throw both of them if they conflict with one another, right? You can also use work ahead log, sorry, not work right ahead logs, and then undo this. We already saw how to undo the transaction. So this one you can assume is just using private workspaces. Okay. Yes. Question.
That again being conflict.
Okay.
At the same time, two transactions.
Okay. Question is, in the previous case, will we have a conflict? So in this case, if you're using optimistic concurrency control, all three transactions are touching the same data item. So by definition, that's a conflict. So the optimistic concurrency control technique will just kill the transaction, right? So this will only succeed if you actually have locks or other some other approach, right? Not because this one will be doing exactly what we said don't happen, which is conflicts are rare. Right? So if you touch the same data item, by definition, it will flag as a conflict.
There's no locking at all.
Okay. Question is, if you have no locking mechanism, how will you track if the same data has been touched by multiple data items? You can do this in a number of ways. So if you have private workspaces, you have your own copy. When you go to merge the changes, you can see which data items you have modified, and then you can go and check if those data items are modified in the database since you started. You can keep a timestamp on the data items and say this transaction began at noon. Okay, this data item was modified after that, and you are this transaction also modified it, so there is a conflict. So you can have many ways to detect it. Okay, we will talk about timestamp based techniques in just a moment. Okay, optimistic concurrency control. Now the rest of the techniques are going to be called pessimistic concurrency control. Okay, the reason they are called pessimistic is they will assume locks are needed. Okay, transaction can conflict at any time. So let's use locks and prevent this type of conflict from occurring in the first place. Okay, you still want concurrency, so you're not going to take like big database locks. You will take fine-grained locks and still allow some concurrency, but you will not let two transactions modify the same data items because you have a lock now. Okay, this will prevent the conflict from occurring. Okay, now there are many techniques that are actually used to implement locking-based concurrency control. A popular one is called two-phase locking. Okay, it is best shown with this picture. Okay, so basically, in a two-phase locking approach, the transaction, okay, has two phases. Okay, there's something called the growing phase of the transaction, where it keeps acquiring new locks as the transaction touches newer and newer data items. Okay, so maybe you touch one record, you get a lock before you make that modification. Then you go to the next instruction, it touches some other data item in the database, you grab another lock. As you touch new items, you will grab locks. So this is called the growing phase. Here the x-axis is time, y-axis is the number of locks held. The growing phase, you keep getting more locks. Right? And then after a while, the transaction has touched all the data items it needs to touch in the transaction. You will essentially not grab any more lock. But once you're done with each of the data item in the transaction, you can start releasing the lock. Maybe you are done touching the New York, San Francisco flight. So you can release that lock, and now maybe you'll then look at the next segment and so on. So you have the shrinking phase where you actually go release the locks. Okay? So you acquire locks in the growing phase, you release lock in the shrinking phase. Okay? There are some additional constraints you can put on this growing and shrinking phase that will prevent deadlocks from occurring. Because the big problem in any locking approach or two-phase locking is deadlock. Okay? I presume you know the simplest case you can have deadlocks is there are two data items, A and B. Okay? The transaction 1 tries to grab a lock on A and then a lock on B. And transaction 2 does it in the opposite order. It tries to get a lock on B and then A. And then you might have a case where transaction 1 runs, it grabs a lock on A, and then you switch to 2, it grabs a lock on B. Now the two transactions are waiting on one another. You have a deadlock, right? So same thing can occur here. You have two transactions in the growing phase. Transaction 1 grabs a lock on A and asks for B, and transaction 2 runs, it grabs a lock on B and gets wants on A, and then you are done. In the time you have deadlock and the system will not make progress. Okay? So just having a growing phase and a shrinking phase does not actually guarantee you deadlock-free execution. You have to have additional constraints that acquire locks in a certain order, in an increasing order, that prevents these deadlocks from occurring. We won't go into those details here. That's how you will write a transactional system. But the basic point with two-phase locking is you have to grab locks. Locks are more fine-grained. They're on individual data item, not on the entire database. That's the only way you will get concurrency. Okay? And you got to do it in a careful way to prevent deadlocks. Okay? We didn't talk about what that careful way is, but you understand at least why there can be deadlock. Okay? So if you do this, then you essentially have a more standard concurrency control techniques that is lock-based. Okay? This is not what you may have implemented in your lab, because concurrency control was not a requirement. You just needed consistency, which means presumably you just got a lock on your order database or something like that, and that's fine. But you will have to realize that that will give you sequential execution. Okay? Because there is no concurrency by definition if you get a full lock on the database. Okay? If you had grabbed locks on individual stocks, for example, not on the entire database, then you would have done something that resembles this approach. Okay? But again, that was not a requirement in your lab, so there's no expectation to do it, but at least you understand how you can implement concurrency now. Is this clear? Okay. So that's two-phase locking. There's a version of two-phase locking called strict two-phase locking. In strict two-phase locking, the growing phase is identical, but then you wait until the end transaction and you release all locks at once. Okay? Much simpler approach than trying to release lock one at a time, because you need to know, the transactional system needs to know that this transaction is done with this data item, the remaining code in the transaction doesn't touch it. So you have to do extra work to know when to release the lock. It's much simpler to have taken all the locks, and when the transaction ends, you release them all at once. This is called strict 2PL or strict two-phase locking. Okay? The shrinking phase is just one step where all locks are released by the transaction. Okay? All right. So I have 2 minutes. I'm going to talk about a timestamp based approach that shows you how you can detect conflicts, and then we'll end. Okay? So in this case, we are going to implement pessimistic concurrency control. Okay? But we will now use the concept of timestamps to detect if a conflict has even occurred. Because the question that you have to ask is, how do you know there is a conflict, and so on. Okay? So, and when you want to abort the transaction. So here we will give each transaction a timestamp. Think of it as a Lamport's clock value. Whenever a new transaction starts, you give it a timestamp, which is the Lamport's clock value. You can even use real timestamps if you want. Okay? Now, if transaction I wants to perform an operation that conflicts with transaction J, and we'll define what conflict means. But if transaction I has a thing that operation that conflicts with J, then you will abort Ti if it has an earlier timestamp, because you'll say a later transaction already modified that data item. Okay? So this transaction needs to abort and restart. Okay? So because you started and someone else has come and made some changes that started after this transaction, so you abort the earlier transaction. Okay? So that's our rule. Okay? Where your transactions start with timestamps, and then anytime you do an operation, you see if some other transaction that started after this transaction have actually made a change to that data item. If so, you declare a conflict and you abort the transaction. Okay? So the question is, how will you detect that there is a conflict? Yeah, the way you will do this is, in addition to having a timestamp for every transaction, you will keep a read and a write timestamp with every data item. Okay? This is same as, let's say, the last modified time of your file or the last access time. Your files have timestamp, right? Whenever you make a change and you write the file, your file system actually updates the timestamp on the file that tells you when it was last modified. Okay? We will use that same approach in the database, where every data item X will have two timestamps. The last time it was read by any transaction and the last time it was written to. When was it last read? When was it last modified? We'll keep these two values. Okay? And then it's very straightforward to actually detect that there is a conflict. Whenever a transaction wants to read X, okay, you are going to basically take that transaction timestamp and see if there is a newer write timestamp. If there is a newer write timestamp, says that item was modified after this transaction started. Okay? So you say that's a conflict. Okay? Because some newer transactions come and modified it, so that data item's timestamp, write timestamp is higher. So you just abort the transaction. Okay? If not, you will perform the read, because now the read is succeeding, and then you will essentially set the max timestamp to be the max read timestamp and the timestamp of the transaction. Okay? So you check it. So this is called a read-write conflict. This transaction is trying to read it, but some other transaction went and modified it. Okay? So if you find a read-write conflict, you say that this transaction cannot be allowed to perform this read, you abort it. Okay? If there's no read-write conflict, okay, multiple transactions can read the data item at once. It's like a read lock, right? So you don't check the read timestamp, you only check the write timestamp in this case. Okay? And then you update the timestamp. Okay? And the write is the opposite. So if you want to write to X, then you are going to check, has any transaction newer transaction read it, or any newer transaction written to it. If there's a newer transaction that's accessed it in any way, you abort the transaction. You say that newer transaction touched the data item, abort this transaction. Otherwise, you perform the write, and then you update the write timestamp to the current transaction timestamp. Okay? So this is checking, is there a read-write conflict, or is there a write-write conflict? You are trying to write, did someone else read it, or did someone else write it? Okay? So this is checking for read-write conflict or write-write conflict. Either of those two conflicts arise when you write, you abort, otherwise you continue. Okay? So this is going to now tell you a little bit about how can you detect when there is a transaction conflict and so on, okay, by actually tracking when transactions modify data items, etc. Okay, all right. We are 2 minutes over time, so we'll stop here and continue next time.